In this lesson, we're going to look at the Poisson distribution, which is a probability distribution for discrete random variables known as the law of rare events. So as you can see in the targets there, we're going to find the probability of a given number of occurrences of what we're going to call a rare event and explain what that means in a given amount of time. And then we're also going to see how the Poisson distribution is actually an approximation of the binomial distribution, or can be used as an approximation of the binomial distribution, and we're going to see why that is. So let's begin. First of all, what is the Poisson distribution? Well, it was named for this Frenchman, and he did his work in the 1830s, and his works revolved around looking at the distribution of the number of wrongful convictions in a country in a certain year. And the work that he did produced this distribution called the Poisson distribution. Interestingly, this work had been done by de Moivre, of de Moivre's theorem that we're going to be studying later in the year as well. And so some people think that this should be called the de Moivre distribution. But what does it look at? What does the Poisson distribution apply to? Well, notice you see I'm here calling it the law of rare events. And rare just means that there are a lot of opportunities for this event to occur, and relative to that number of opportunities, it doesn't occur all that often. So, wrongful convictions, right? You look at the number of phone calls to a call center in a minute, you might think, well, that's not very rare. Call centers get phone calls all the time. But when you consider the number of people that could be calling that call center, it doesn't happen very much from that perspective. So if there are, 300 million people in the United States, and they all have the potential to call some call center in, Virginia somewhere, most of them don't, right? It'd be pretty rare to find someone that did. So even though that call center, from the perspective of the operator is getting calls all the time, it doesn't seem very rare. From the perspective of looking at the opportunities of calls that could be happening, it's a pretty rare event. You can see the next one, number of mutations in DNA subjected to a given amount of radioactivity. And interestingly, the last one I have here is the number of soldiers in the Prussian army killed by horse kicks accidentally in a year. And this is actually one of the most famous uses of the Poisson distribution in 1898 by a man named Ladislaus Bortkiewicz. And so he did some work about trying to figure out how many soldiers in the Prussian army would be killed accidentally by horse kicks. And that was one of the most famous early uses of the Poisson distribution. So let's look at how the Poisson distribution came about and how it relates to what you already know about. And it relates to what you already know from the binomial distribution. So you can see here I've put the binomial distribution on the screen. We've got n choose r times the probability of success to the r successes. So n was the number of trials, right? P was the probability of success. R was the number of successes. And then we're also multiplying by 1 minus p times the number of failures, if you will, right? And so just, absorb that for a second. Remember where all that came from. Given R and P and N, we could tell the probability of exactly that many successes. Well, what we're going to do is imagine, I said that the Poisson distribution is what you get when there are a lot of possible opportunities or a lot of trials, right? So what we're going to do is take the limit of this as the number of trials approaches infinity. Okay, so you can see I'm letting n, the number of trials, approach infinity, and just applying the formula, right? Now, let's continue with that. If you look at what we've said as far as what the variables represent, n being the number of trials, p being the probability of success, and r being successes, and you remember what you know about the binomial distribution and its mean, that is to say, the mean is the number of trials times the probability of success. So the mean number of successes is NP. The expected value is NP. Well, we can conclude from that that the probability of success is just the mean divided by the number of trials. And again, this is only for a binomial distribution, but that's what we're looking at over here is a binomial distribution. So what I want to do is go ahead and replace P with the expected value over the number of trials. And that's what I've done here. So in each of these two instances of the variable P, replace that with mu over n, And so nothing fancy going on here. But this is only going to work for a binomial distribution. Okay, now we want to take this expression and start to kind of rearrange it a little bit in a way that's going to help us simplify things. So first thing I'm going to do is this. Now this might look a little confusing. All I've done is taken the combination and wrote it out, right? So here's the combination written out in this definition, and then I've just applied the exponent to both the numerator and denominator, okay? This is the part that might be confusing if I don't explain it. So I'm going to rearrange these fractions, and I'm going to move the r factorial underneath the mu to the r, and I'm going to take the n to the r and move it to the first fraction. So I'm just rearranging the factors in the denominator here. And so what we get when we do that is nothing is, oh, on the next page, sorry. So on the next page, you'll see I have this here, okay, and I've just pulled the n to the r, which was over here, to this fraction, and the r factorial to this fraction. Additionally, I've canceled out all the factors in the n minus r factorial. So this n minus r factorial, I've canceled them out of the n factorial. Right? So all I have at the numerator now is n times n minus 1 down to n minus r plus 1. Okay? So make sure that makes sense. If it doesn't, I can't answer your question anyway, so sorry, you'll have to talk to each other. But moving on. Okay, so I've got this n minus r exponent. Let's just break that into a positive n exponent and a negative r exponent, right? We know that when we multiply, we add exponents if the base is the same. And so we're just reversing that rule here, where we're breaking that up. We've got a subtraction of exponents. I'm going to put that there, okay? Now, some of this might start to look a little bit familiar, maybe, because this expression and this expression simplify quite a bit, as does this. Okay, now I kind of just gave away the answer here, but let's look at why this is happening. Well, we can see that mu to the r over r factorial is just coming straight down, but I've written a 1 as a factor here. Why is that? Well, remember, we're taking a limit, right? We're taking a limit as n approaches infinity, and I kind of remember from calculus how to evaluate limits. I asked Mr. Scheffler, and he helped me with this. And I see in the denominator here, I've got n to the rth degree, right? N to the rth degree. And I remember, you know, if I have a fraction of a rational expression of powers of a variable, and I'm taking that variable to infinity, that if the bottom degree is greater, then that fraction goes to 0. If the top degree is greater, then that fraction grows infinitely. But if they have the same degree, it's the ratio of their leading coefficients. Well, interestingly here, I had already canceled out all the n minus r factorial factors in both the numerator and denominator, and so I'm left with this. But how many n's are there if we multiply this out? N times n minus 1 times n minus 2 times n minus 3, ding, 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 all the way down to n minus r plus 1 here. Well, how many is that? That's our things, right? This is r factors. You can take a moment and sort of count them in your head, but pick an r and convince yourself, right? This is r factors. So if I multiply this out, what's the leading coefficient? If I just multiply the n's, I get as my first term in that expansion n to the r, right? And so yeah, I'm subtracting things from that, but the limit as n goes to infinity of n to the r minus, I don't care what the other terms are, over n to the r is just 1. And so this is 1, right? So that evaluates nicely. This, if you recall, maybe I should do this on a different sheet, is related to E in the following way. If you remember, one of the definitions that you probably learned for E is that e is the limit as x approaches infinity of, and if you didn't learn this, don't worry, we'll be talking about e plenty in the future, of 1 plus 1 over x to the xth power. Okay, and as we increase x, we get closer and closer to e, and this is so this is one definition of e. Now, how does this relate to the expression we just wrote here? Well, we've got 1 plus negative mu over n to the nth. Well, I can see x here is the same as my n. N is going to infinity just as x did in this expression. So replace x with n and replace the 1 here with negative mu. Well, what do we get when we do that? This is actually x to the first power, right? So e to the first, excuse me, not x to the first, e to the first power. So e to the first, that's coming from this 1. And like I said, we'll talk more about that later in the course, but if we replace 1 with negative mu here, then this expression will produce for us the value e to the negative mu. So this is e to the negative mu. Great. And now I've got this expression, and I'm claiming that that's a 1. Well, let's think about what's going on here. This is, basically 1 over this number to the r, right? But this is going to infinity, okay? Now, mu is a constant, and so we're dividing a constant by infinity, by a number approaching infinity or tending towards infinity, and so this expression is approaching 0. And 1 minus an expression approaching 0 is an expression approaching 1, and 1 to this is a constant, right? R is the number of successes, it's a constant. 1 to a constant is 1. So a number approaching 1 to a constant is approaching 1. So this limit, as n is approaching infinity, is approaching basically this expression. Okay, now that expression is the Poisson distribution. So the way we write the Poisson distribution, we've got this expression e to the negative mu times mu to the r over r factorial, where mu is the expected value and r is the number of successes. We say that x is Poisson distributed, or x is a discrete variable that follows the Poisson distribution, so PO is for Poisson, of lambda, where lambda, and this is just, don't let this confuse you, this is just typically how it's written, lambda is the expected value. So they've just done a variable change on us. Don't ask me why, I don't know. But we've got mu, we're recalling mu lambda. Lambda is the expected value. And if x is distributed that way, what that means is that the probability that x is any certain value is equal to e to the negative lambda, e to the negative expected value, times the expected value to that number of successes or occurrences, divided by that number of occurrences factorial. Okay, so this, this here is the Poisson distribution that you should know and expect to use. Okay, and this is what you'll see in the literature, as it were. Now, again, lambda is the expected value, but interestingly, in a Poisson distribution, not only is lambda the expected value, and this might be the reason for the change of variable, but lambda is also the variance. So in a Poisson distribution, the variance and the expected value are the same value, and it's that lambda. So this is how the Poisson distribution comes out of the binomial. We just take the limit as n approaches infinity, and we start to evaluate. So in the next video that's available to you, we're going to look at some example problems. So make sure this makes sense to you, and then go and look at the example problems. Fortunately, we don't actually use this too much because the calculator can do it for us, and I'll show you that as well. Until next time.